Hope you're all having a good day. Today I'd like to take you through the topic of reactance of capacitors and inductors. Let's start off basic. What is reactance? Reactance is the opposition to a change in current or voltage, similar to resistance but in the case of AC circuits. I compare it to resistance because I like to think the two topics go hand in hand. More on that later. For now, let's delve deeper into what an AC circuit is. In an AC circuit, the current changes direction periodically, as opposed to a DC circuit, where current flows only in one direction. The typical behavior of resistors and resistance that we're familiar with arises in these contexts of DC circuits. AC circuits, on the other hand, involve not only resistors but inductors and capacitors too. Let's delve into the behavior of these components in AC circuits. As observed on the left, in the case of inductors, voltage leads and current lags, while as observed on the right, voltage lags and current leads. This difference in leading and lagging can be described as a phase difference. In both cases, the phase difference between the current and voltage are 90 degrees or pi over 2 radians. This occurs because of how these components store energy. Inductors store energy in a magnetic field, resisting changes in current flow, while capacitors store energy in an electric field, resisting changes in voltage. In the case of DC circuits, current flows only in one direction, and so there is no phase difference between voltage and current, and the energy is simply stored as internal energy in the resistor. Understanding this phase relationship helps us better grasp the concepts of reactance and impedance. Reactance of capacitors and inductors. The reactance in inductors, or the inductive reactance, is given by omega L, or 2 PIFL, with the inductive reactance being proportional to frequency. This means that with an increase in frequency, the inductive reactance increases, and so current will subsequently decrease. Conversely, the capacitive reactance, given by 1 over omega C, or 1 over 2 PIFC, is inversely proportional to frequency, meaning with an increase in frequency, there is a decrease in capacitive reactance and an increase in current. In the case of a combination of these devices, whether that's 2 or 3 of them combined, the reactance and resistance add up, and this combined opposition to current is called impedance, given by square root of XL minus XC squared plus R squared. Another relation between the three is given by the phase angle, derived from the impedance triangle as seen on the slide, where phi I equals tan inverse of XL minus XC over R. Let's solve a few examples and apply the concepts we've just learned. Given in this question about inductive reactance is the inductance and the frequency. We know XL equals omega L, we have L and need omega. We know omega equals 2 PIF, which gives 6.283 times 10 to the power of 3 radian per second. We can now find the inductive reactance. XL equals omega L, or 6.283 times 10 to the power of 3 radian per second, times 4 Henry equals 2.5, 1 times 10 to the power of 4 ohms, or 25.13 kilo ohms. In this similar question, we're given the capacitance and the frequency. We know XC equals 1 over omega C, we have C and require omega. Omega equals 2 PIF, which gives 6.283 times 10 to the power of 6 radian per second. XC equals 1 over omega C equals 1 over 6.283 times 10 to the power of 6 radian per second, times 0.01, times 10 to the power of minus 6. Farad equals 1 over 0.0629 equals 15.91 ohms.